This is the second lecture on acids and bases, equilibrium. And we're going to continue where we left off last time. The idea that we were talking about pH and relationship between concentration and these P values. P is just, again, an easier way of discussing it. And whenever you see that, just know that you're going to be taking the negative logarithm of whatever you happen to be talking about. And we can have this conversation in regards to POH, which we typically don't do because we have pH and we're used to that one. But it's also the P of, we can do it of Ka values or Kbs or Kws. We'll get more into that as we get there. So we already kind of discussed this. I won't go into it any further in regards to relationships. You can look at it on your own. Other ways you can measure pH, I think this is on the test, or I've seen it somewhere. Other ways you can determine what a pH is one is this litmus paper, which you probably did somewhere along the line in middle school in regards to color, what these things look like. Another way you can do it is looking at voltage potential energy differences. It's just a meter, which is a pH meter, and we'll use those in class as well. And it's just one way of looking at it electronically, what pH could be. So strong acids, we've talked about that in class. There's 7 of them. You should remember what those are. And how do you define what is a strong acid? It's something that completely dissociates in water. So if you want to look at it from a Ka, an equilibrium expression, this doesn't have an equilibrium. It goes to completion in forming products. It does not go the other direction. No. It goes all the way to products. So it forms electrolytes. Strong bases do the exact same thing. So we're taking a look here. It says those are the ones that are soluble. They're heavier than the alkalis, and you're typically looking at these further down the list, type or group 2s and all of the group 1s. So as an example, you can have things like sodium hydroxide and the heavier group 2s. So calcium hydroxide as an example. The other ones work as well too. So these guys will dissociate completely. So just notice, for example, that something like magnesium hydroxide does not completely dissociate in water. So that's going to form a bit of a mixture. So again, looking at these Ka, I'm saying it ahead of time, expressions, we have these which are equilibriums, but notice we're just changing the little variable there from a Kc to a Ka. So we're looking at it more from an acid-base perspective. So this case, it's an A. Looking at how some of these associate. Remember, strong acids go to completion, so it's a large value in the numerator. So it's usually close to like 1 or higher, I guess. But for these over here, look at how they're relatively low. They're meaning that I have more reactants than products. When I'm looking at these Ka values, they're all, they're present. They do dissociate, but it's not a whole lot. It's very little. The one that seems to come up quite a bit is acetic acid, and let's see if I can see it on here. I don't. It's in the base group. So acetic acid is the classic example of something that associates, but not a whole lot. Okay. So here's a little problem for us. We have a concentration right here of formic acid, and we have a pH value of it right here. So it says calculate the Ka, and this is one of those you're going to see a lot of type problems. So it's asking us to calculate the Ka for this at some given temperature. So here's our expression right here. We have the pH, and the pH really is an expression of this. We just have to turn it around. So remember, when this formic acid is going into solution, it's forming these two products equally. So if I know one, I know the other. Okay, so let's see how that kind of shakes out in a rice table. So we're putting these values here, so now I know what the concentration of those two products are, and here's our rice table. So we have this initial concentration of the formic acid, and that was given in the problem. We know that this is going to associate into these two products equally. Initially I don't have any, but after a change I'm losing this much of my reactants, and I'm gaining this much of my two products. So let's see how that's going to affect the others as the change goes into place. So here's our change after we've gone through change that much, appreciably to 2 sig figs. We're still 1.0 molarity. And then we have this change over here. So we're ready to put into our equilibrium expression. It's all done. So when we take a look at it, we have this set up here, and then we end up with a Ka value of that. So that gives us the answer. We know what the dissociation is for this equation. Now to look at the percent ionization, we'll talk a little more about this in class, whether we can just ignore that subtracted value or not. When we look at how much this dissociates, we do have a value given right here, the Ka value, the dissociation value of the hydronium ion. And we have the initial concentration. So if we look at how much is actually dissociating and creating an ionization, we can look and just divide the ionization by the initial concentration, multiply times 100%, and this is the value that actually dissociates out. So it's just another expression of looking at this type of scenario. Alright, so another type of an example here is if we want to figure out the pH from the Ka, so we're given Ka to start with. In this case, we know the value, it's right here, and it's acetic acid, so you'll get used to seeing that value. It comes up quite a bit. And I have an equation listed over here. For some reason this isn't lined up. It should be a little arrow sitting here and an arrow sitting there. So we can see that we have our products over reactants, and we have to again go back to our rice table to figure out how we can do this. So again, we have an initial concentration of acetic acid. So here's the equation. Here's our rice table, initial concentration. Remember, we're going to be moving in this type of a scenario, so I'm going to be losing. We'll go ahead and just put the variables in. I'm going to be losing some amount, I don't know what it is, and I'm going to be gaining equal amounts of X on the other side. And I have this equation to work with. Okay, so if I subtract that off, we are going to make an assumption that the amount that X is negligible in comparison to the original amount. So we're going to say ignore it. But this value I will not ignore because, well, that's what we're really trying to figure out. So if I multiply those two, I'm going to get an X squared, and we'll see how that shapes up here in the equation. So there's our setup. We had the Ka value sitting right here, and then if we simply solve for X, we find that the concentration of X and the acetate ion are equal to that. And then I can go back and figure out the pH of the solution is by putting in a negative log. Done. You'll see lots of examples like these in class and in the homework. Just looking at some various Ka and Ka1 and 2 values for some polyprotic acids. These are acids that donate more than once or have the potential to donate more than once. So just to use ascorbic acid as an example, it can donate 2 hydrogens. Carbonic acid can donate twice. But notice the important part is after it is donated once, this Ka value as an example, notice how little it donates a second time because that second or third hydrogens are held more tightly because of the resulting nuclear force of attraction onto it. Okay. Weak bases, we can look at it from this standpoint. It's kind of the same idea, just different. If I want to look at ammonia as an example, that is a base, and it can attract hydrogen ions to it and result in a conjugate acid. So again, bases turn into conjugate acids, and acids turn into conjugate bases. So same idea. The only difference is that we're forming hydroxide ion instead of hydrogen ions. And the principle works exactly the same, you just have to change your perspective. In this case, we're going to call it a Kb expression. So ultimately, we may be getting a POH, which we'll see here a little bit later. Some examples of some very common bases. Notice as an example, this is the exact same value that we saw for acetic acid. So again, it kind of sticks. So 2 very common weak acids and bases. Acetic acid and ammonia, those are the values that go along with it. Okay? Well, good place to take a break, and we'll do one more lecture for chapter 16.